Hello and welcome. Today we are going to be doing an introduction to statistics. Now there's a lot of writing here and this does get a little bit long, but hopefully there's a fair amount of this that you might already be somewhat familiar with. It shouldn't be all entirely new. So let's get going here. So statistics is the study of how to collect, organize, analyze, and interpret data collected from a group. There's two main branches of statistics. One's descriptive and one is inferential. Descriptive statistics is a branch of statistics concerned with the collection, organization, and analysis of data. Whereas inferential statistics is the branch of statistics concerned with generalizing or making predictions from the data. I like to think of it as kind of like this is the past. This is explaining something that happens, and this is making something, making a guess or an idea about the future. Now, it's not always making a prediction about the future. We also make predictions about the population, current population, stuff that we don't know about. We're making predictions, but that's one way that I kind of think about it. Statistics is describing something that happened. Sorry, descriptive statistics, describing something that happened, and inferential is making a prediction about maybe something we don't necessarily know. The first step in performing a statistical study is deciding who or what is being studied. So we have individuals, which is a single person or object that we collect data from. And then we also have a variable. The variable is the measurement or the observation of the individual. Okay, so we might ask a person what their favorite color is, right? So the person is the individual, the variable might be the color, or how many hot dogs do you eat when you go to a hot dog eating contest? So that's a variable that's going to change from person to person. The population is the set of all the items or all the people of interest. Oftentimes, we're not able to get information from an entire population. We can't ask every single person what their favorite color is. But what we do is we can take a sample, and that's just a subset of the population. So we ask a few people, and if we ask the right people and we're careful with how we select those individuals, then hopefully our sample represents the whole population. We'll look at some good ways to sample and some bad ways to sample in a minute. So for these next couple problems, let's identify the individual, the variable, the population, and the sample for each of these. So make sure to ask yourself what question is asked repeatedly and what changes each time the question is asked. Stacy asks her husband if he thinks she owns some nice clothes. So her husband looks at what she has on and says, "Hey, your outfit is beautiful." Stacy then tries on 3 more outfits and asks her husband their opinions of each. So in this case, the individual, you might think it's Stacy, but the individual is actually one outfit, right? And then the variable, that's going to be the quality of the clothes that she's wearing. Like, is the outfit beautiful or not? So we'll just call that the quality. The population, what we want to know about is if we want to know about all of her clothes. So all of Stacy's clothes. And then the sample, remember, she had on 1 and she tries on 3 more. So that's a total of 4 outfits that she put on a little show for her husband and said, "Hey, what do you think of this? Hey, what do you think of this?" So what question is being asked repeatedly? Is this outfit beautiful? So that's our variable. The sample ultimately was asked 4 times, and so that's why there are 4 total outfits that were viewed. Next, we have a facility manager wants to know if the employees think the building is too cold. So he asks the office manager how she feels about the temperature. Then he asks her assistant the same question. So the individual would be the people that work there, or specifically one person at a time. The variable is going to be their opinion of the temperature, like what's changing every time. Does somebody say, "Yeah, I think it's cold," or they say, "No, the temperature is just fine." So what changes might be their opinion. That's going to change from individual to individual. Now, the population that we want to know about are all the people who work there. but it's very difficult to ask all the people. So instead, we only ask a couple. We take a sample, and the sample would be the two people that ultimately were asked, the office manager and the assistant. Now, there are different types of variables. So there are two main types that we're going to be talking about. Qualitative variables, sometimes called categorical variables, and they describe some quality of the individual. Qualitative variables might be like things that aren't responded to with a number. So like favorite color, like colors are oftentimes categorical, right? Favorite type of food. When you respond with something other than a number, it's qualitative or categorical. You'll hear me say that a lot too. And then we also have quantitative. I know qualitative and quantitative sound very similar, but quantitative variables are sometimes called numerical variables, and they're numbers that represent something. These are questions that would be answered how many, right? How many hot dogs did you eat? How many video games did you play last night? How long were you on your phone last night? So these are quantitative. Qualitative, like I said, is your favorite color, your hair color. Now, what's interesting is categorical variables, like what's your favorite pet, right? A cat, a dog, a rat. Um, Qualitative or categorical variables can actually be numbers, but we don't often think of them that way. For example, um, you could say, what's your zip code? And so I live in 850, oh wait, that's my old zip code. 85032 is where I used to live, right? And so I responded with a number, but that's like a whole category of people. Or I could even say like, my birth month was is 8, right? So I was born in August. And so even though I might respond with a number, it's not necessarily quantitative because that doesn't really answer the question, how many? So just be aware that there is a little bit of gray area there. You can't just say like, oh, it's a number, therefore it's quantitative. Sometimes numbers aren't. Phone numbers, also birth dates, we don't usually think of those as quantitative. Social security numbers, things like that, even though they're numbers, those are more categorical, was kind of how we use those. Let's identify whether each one is qualitative or quantitative. Okay, and by the way, I'm perfectly fine personally if you were to even say categorical. That's totally fine if you don't like the idea of qualitative and quantitative. So a dog breed, that doesn't answer how many, so therefore it's categorical, or in other words, qualitative. I was just looking to make sure I spelled that right because that would be embarrassing. Oh well, I've done a lot of embarrassing things before. Average rainfall in your city. Now that is responding with a number. It's an amount, and so it's quantitative. The number of customers at a restaurant. Well, right away we see the number of customers. When we see that, that's going to be quantitative. And then eye color, you would respond with a color that's categorical, or in other words, qualitative. So either one is fine. Quantitative variables do come in several forms, right? So discrete data can only be certain values. Normally we think of these as whole numbers. Like the number of people is typically a discrete value because you don't really have half a person, or you don't have 0.7 of a person. It just depends. If you're talking about an average, that's different. But in general, discrete are when we want to count things, and it often represents just things that can be counted, right? Whereas continuous data can take on any value and even decimals. This type of data often represents things that must be measured, right? So if you want to talk about your height, that's usually not discrete because we have all of those fractions, all of the in-between amounts, right? If we can measure time, time is often continuous. So if you can have numbers in between, then it's continuous. If it's very rigid and it's just like 1, 2, 3, 4. That would be discrete. Okay. So let's go through and look at some examples of continuous and discrete. The distance between two objects. Well, the distance between two objects is going to be continuous. And so an example might be the distance between these two desks is 3.5 feet. Right? What about the number of shirts in your closet? Well, the number of shirts in your closet we would count by whole numbers, and so that would be discrete. I own 12 shirts. I own a few more than that, but I probably should give more away. I need to clean out my closet. How many times you've washed your hands today? Well, think about this. Do you wash your hands a whole number of times, or can you can you wash your hands 2.7 times? No. So that means there's it's a very countable number, which means it's discrete. I washed my hands 4 times today. The amount of time that you spend on your phone. Well, time is generally continuous. It just depends on how small of units that you want to measure. If you go and check on your phone, this is actually a good thing to do. We'll explore it more later, but you can go in and see how long were you on your phone today. So might be, I checked mine yesterday. I was on my phone 1 hour and 52 minutes, and that's pretty close to my average. I've been trying to cut back on that, spend a little more time with my family, a little more time out doing stuff. Let's go ahead and look at something called surveys. The most common way that data is collected is by questioning or surveying a sample of a population. In a survey, the variable being measured needs to stay the same from individual to individual within the sample. In other words, you're going to ask the same question or questions to everyone that you talk to, or however it is you're collecting your data. We're going to explore 6 different methods for looking at how to sample. In each of the sampling methods, we're going to answer the question, what is your daily average screen time in hours? Okay, so that's what we want to think about here. So first, we're going to look at the most basic, called a simple random sample. Some people in the statistical world, they'll even just call this an SRS because it's so common. We use it all the time, so we oftentimes shorten things down when we use them a lot. An SRS, or a simple random sample, occurs when every individual in the population has an equal chance of being selected. It can be a little bit more than that, but that's pretty good. The best way to think about this is names in a hat. You write everyone's name on a piece of paper, drop it in a hat, mix it around, and you pull out however many you want. That's the simplest, most basic way to think about what a simple random sample is. Okay, we can also use a random number generator for that. So random number generators, also called RNG, is a great way. You assign everyone in the population a number, and then you use a random number generator to select however many numbers you need without replacement. I just found out the other day that my kids play video games, and they just kind of say things like, "Oh man, you got a bad RNG," and I was like, "Do you even know what that means?" They're like, "Oh no, it's how the map was made. It just means it's a bad map, Dad." I'm like, "Well, RNG stands for random number generator." And they're like, "Oh, well, yeah, I knew that. But in Minecraft, it just means you got a bad map, bad RNG." I was like, well, yeah, I guess. So describe how you would collect a simple random sample to answer the question, what population you would use. So if we want a simple random sample, like I said, you could assign everyone a number and then use a random number generator to select the people without participants. I chose to just say this. If we wanted to know this for all GCC students, okay, so my population would be all GCC students, if that's what I want to know. Then we could get a roster of all the GCC students and assign them a number from 1 to n, use a random number generator to select 100 numbers. And then I probably want to be careful and say without repeats, because we don't want to choose the same person twice. And then we contact those 100 people and do that. Now, I was thinking originally that, just drop all the names in a hat. But, there's like 20,000 people that go to GCC. That would be a very big hat and very time consuming to write out 20,000 cards and shuffle them all up, mix them up. So this is probably a little bit better. We could do it that other way though. Writing all the names on index cards, put them in a giant barrel and roll it around and then pull out 100 of them. That seems like a lot of work. There's also what's called a systematic sample. A systematic sample occurs when individuals are selected at regular intervals, such as every nth individual, or you could think of this, I write nth to be in general, but you might say like every 10th person or every fifth person to walk in the door. And so this would happen a lot, maybe like in a factory. Maybe they would take like every 100th item off for testing to check for quality control. Or you could even do this like once an hour, like every hour at the top of the hour, we're going to pull one item off and we're going to sample it. So systematic sampling is relatively easy to do because you just find some place to start and you go every fifth person or every 10th person or once per hour. So whenever you see that, that's how you would identify systematic. So if we want to collect data to answer the question, our same screen time question, what we could do is I could stand at the entrance to the student union between 9 and 11 a.m. on Monday and ask every 10th person to show me their screen time. Now, the question that I would ask you is, does this represent the population? So is this getting at the heart of answering the question that is this covering all GCC students? If our population is all GCC students, standing in the middle of campus and asking them this seems like a good idea, but there's a problem here. And you don't have to write all this down, but this is kind of important to understand. While I might want the population to be all GCC students, I don't actually have the chance of getting all the students. Students who are online only or take classes in the evening, or students who rely or are only on campus for who are only on campus for Tuesday and Thursday classes, they don't have a chance at being selected. So I need to come up with a better way to sample if I really wanted the population to be all GCC students. With the one that I have, my population is actually GCC students who take classes on Mondays and Wednesday mornings, or are on campus on Mondays. This is actually something called under coverage in statistics, and it just means that, we didn't actually have a chance to ask all the different types of people our question. So it's just called under coverage, and you try to avoid it. So while we did come up with a method for systematic sampling, it's probably not a good method if we want our population to be all GCC students. Stratified sampling occurs when the population is divided into groups based on shared characteristic, and a simple random sample is taken from every group. Okay, so what that might mean is if you wanted to know about whether or not a particular game was good and you thought that maybe different age groups might have different opinions, then you would want to take a sample from all different age groups. If you were going to pass a law and you thought that it might be split based on people who are parents and they have kids, and people who don't have parents, if you think that there might be a discrepancy between there, then you would want to make sure that you sample from both groups. If you were going to try to pass something for schools, then you definitely want to think like, okay, I definitely need to sample some people that have kids and some people that don't have kids, because those people that don't have kids, they still vote as well. So a stratified sample is when you identify the different groups involved and make sure that you take some people from every possible group. And this same question that we've been asking about cell phones, well, I think that maybe age groups is probably a good thing to stratify based on. We could let the population be all the students in our class. Um, I did this for reasons, but then what we could do is we could say, let's split the class into two different groups. Students born in 2003 and earlier, or in other words, kind of the older students, and students born in 2004 or later, so younger students. And you could put everyone's name in a hat from 2003 and earlier and draw out 5 names, record their responses, and do the same for the ones that were born in 2004 and later. Again, we're splitting them up based on age because I think that your age may have an impact on your screen time. Because of that, I want to make sure I get some young people involved in my sample and some older people involved in my sample. So I'm stratifying based on age in that case. Next, we're going to look at cluster sampling. A cluster sample occurs when you have similar groups or clusters and they're randomly selected and every individual within that cluster is sampled. Okay. Cluster sampling does get mixed up with stratified sampling sometimes because in both cases we're looking at some different groups. Stratified sampling is when you take some from all groups, some from all, whereas a cluster sample is when you take all from some groups. I know that might seem a little bit weird, but let's look at our example here. A really, really clean example of a cluster sample is by randomly selecting several classrooms and surveying every student in those classrooms. Cluster sampling is also sometimes called an area sample. And that's because you kind of go to one area and then you get everyone from there. And as long as you do this in a good way, this is an easy way that you can collect a lot of data. And if you're careful about how you select your areas, then it's great, right? And so describe how you would collect a cluster sample to answer the screen time question. Well, what we could do is if we want to know, let's let our population be all students who take math at GCC. We could have made it all GCC students, but I just wanted to do this to change it. If we get a list of all the math classes at GCC, write them on slips of paper, drop them in a hat, mix them around, and draw out 5 papers, and then we collect our data from every student in those 5 classes. Again, that's all the students from some of the classes. We go into the classroom and we get everybody there. We get all 20 of them. We get that cluster. Okay, so cluster sampling does work well when each cluster looks kind of like a little mini microcosm of the whole population, right? All of those classes that we have, they are all math students here at GCC. So that's when cluster sampling works well, when you have each of the clusters looks kind of like a little mini population. Convenience sampling. Now, a convenience sample consists of individuals who are easy to reach or they're readily available to participate. A convenience sample sounds really great. You're like, hey, that's very convenient. It might mean like, hey, just asking all of your friends or asking all of your classmates or asking all the people close by you, hey, what's your screen time? What's your screen time? I want to get this done as fast as I can. That's called a convenience sample. If we were going to do this with here on campus and have maybe not just ask our neighbors, what I could do is stand outside the math building right before class and say, oh man, I got to get this done. I'm just going to ask the first 20 people that I see what their screen time is. So one way that you can identify a convenience sample is if you ever see this, the first 20 or the first 100 or the first 50, that's usually a convenience sample, okay? So the first 20 people might all have something in common. Maybe they're all very timely. People who are arrived to class early tend to be more organized and you know spend their time maybe not on their phone because they have too much stuff to do. They're the busier people and they're not on their phone as much. So convenience samples don't often represent the entire population. When you do a convenience sample, a lot of times you'll get answers that do not represent the population. Convenience samples really should never be done if you want to do something serious with your data. Also along the lines of something that should never be done is called a voluntary response sample. This is when individuals choose themselves to participate. Now, some people get very confused by this because, like, if I come up to you and ask you a question, hey, would you tell me your screen time? Some people think like, oh, I'm volunteering to tell you, I'm volunteering to answer that or not. No, 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 no. If you're chosen to participate, if someone comes up to you and says you've been selected to participate, that's not voluntary response. Voluntary response is, look at our example, I guess. A voluntary response might be if I post a link and just says, hey, tell me your screen time. And then you have to choose, like, oh, hey, look, there's a link. I'd like to tell them my screen time. Right. So another example of this would be if I stood outside the student union with a sign and the sign just says, how long are you on your phone? And anybody that comes up to me, they come up and show me their phone, they would then be a part of this study. That's voluntary response, and it is very, very inaccurate. Unfortunately, this is one of the sampling that you guys are most exposed to if you ever watch TV or you look online, because news channels do this all the time. I listen to sports talk radio all the time, and they have polls, they have online polls that you can choose to participate in. One of the problems with this is usually only people that are really passionate about this one way or the other tend to participate. Also, your audience, like if you're listening to Fox Sports Radio, or if you're listening, or let's do Fox News, that's probably even more controversial. And it says, hey, is this new liberal law a good idea or not? Well, you're going to get like 90% of people that text in or that go to the Twitter and say this is a terrible idea. It's because your audience doesn't represent the whole population. Your audience is already self-selected because they're choosing to watch this type of show and then they're choosing to participate. So voluntary response surveys really are pretty worthless. They should be for entertainment purposes only. Voluntary response surveys do not represent the population. They should not be used for serious questions. All right, next we're going to shift gears from surveying to experimenting. So there's two basic types of experimental studies. One is called an observational study, and they don't manipulate the variables. Instead, they just watch. There's no real impact. They don't do anything, right? If you're a big Star Trek fan, it's like they they used to say things like to come down and to just watch the people but not really interfere with them, right? All they would do is observe. Experimental studies or experiments involve the manipulation of at least one variable. This manipulation is called a treatment. And within an experiment, there are usually two groups. First of all, we have the control group that doesn't get any treatment. That way you can compare whether your treatment is good or not, how it affects the group. So you keep one group the same, and then you take another group and you're going to provide a treatment to them. Now, sometimes the first group, you might give them a fake treatment known as a placebo. You've probably heard things such as the placebo effect. It is real. I would strongly encourage you to just Google search a couple videos on the placebo effect and the power of the placebo effect. There's so many fascinating videos where sometimes people will be given a sugar pill and they'll say this is a new headache medicine and this is groundbreaking technology and we are plan on charging $5 per pill for this because it's so good. We'd like you to take this next time you get a headache and let us know how good it was. And if people believe that this is something really good, they actually respond to it and their body responds to it. And so that's the power of the brain. So, in order to account for this, a lot of times scientists will have two treatment groups, and one of the groups is going to receive the new medicine, and the control group will, we call it a control group, but they will receive the placebo. Like their treatment is to get an inert sugar pill or whatever that placebo may be. Like something that is not the treatment. So they do that so as to compare. Uh, and yeah, I would really encourage you to take a few minutes to look that up. There's fascinating things about human psychology. Let's go ahead and explore what this uh, about experiments. A fitness researcher wants to test whether a popular pre-workout supplement improves exercise performance. So a group of 20 adults who regularly work out are selected. 10 participants take the pre-workout supplement for 4 weeks, while the other 10 take a placebo. All participants follow the same workout routine, and then at the end of the study, the maximum number of push-ups completed in 1 minute is recorded for each person. So we have to ask ourselves, is this observational experiment or, an observational study or an experiment? What was happening here is an experiment. That's because they gave them a treatment. There is a pre-workout supplement. What adjustment could be done to turn this into an observational study? Well, don't assign a treatment. Just let the people take it if they want, and then let them work out if they want, and record the number of push-ups. Like you kind of step back and watch, and you see how many push-ups they can do, whether they chose to use the pre-workout supplement or not. See, experiments are great for showing cause and effect, but sometimes it's very difficult to perform an experiment, like to assign a treatment. For example, the notion of cigarettes, we didn't necessarily know they were really bad for us for a while, and it wouldn't be ethical to take two groups and say, okay, you 10 people start smoking and smoke 3 packs a day for 10 years, and you 10 people don't. Like that type of an experiment isn't really ethical, and we can't do it. So instead, what we do is we just step back and watch. And for a long time, we just watched and looked to see what would happen when people smoked. And we found out that people who smoked had a much, much higher incidence of lung cancer. So that was that was many observational studies. All right, the participants who received the placebo represent what group? Well, that would be the control group, and the participants who got the pre-workout supplement represent the treatment group. All right, next we're going to look at displaying qualitative data. Now remember, qualitative data is also categorical data, not quantitative data, not numbers. So categorical data is what we're going to be looking at. Qualitative data is categorical by nature. Charts and graphs can be used to display the frequency or the relative frequency. So the frequency of it is just the number of entries. It's the raw number, whereas the relative frequency is that number divided by the total number of entries, right? That's where we get into a fraction or a probability. So it's one thing to know that 15,000 people like Pokemon. It's another thing to know that 5% of the whole population likes Pokemon. So it's important to know either the size that you're working with, or in some cases, it's just better to know the relative frequency. That way you can break it up into proportions or percentages, and our brains work pretty well with those. The most common ways to display qualitative or categorical data is with pie charts. Pie charts Mhm. Pie charts divide a circle into pieces and display the relative frequency of each one. Bar graphs can display the frequency or the relative frequency using the length of the bars. So let's go ahead and make a pie chart. In a survey, 300 people were asked which of the following colors was their favorite. They're given the options of red, blue, yellow, orange, green, or none of the choices. Construct a circle graph or a pie chart to represent the data from the table below. You can see here we do have a data table, and our data table that we have just has each color and then the corresponding number of people that like it. So what we'll do is we'll change this from raw numbers of people into the relative frequency, or in other words, like a percentage. The first thing that I would look at is saying, well, I see there's 300 people total. So to find that relative frequency, this would be 78 over 300. And if we go to our calculator and just do 78 divided by 300, you can see we get 0.26. So that means that 0.26 or 26%. We'll do the same thing for blue, which is 12. Oh, I said 30, but I think I said 300. Anyways, it's 12 divided by 300 for this. Once again, when we go to the calculator and we do 12 divided by 300, we get 0.04. So 0.04 is just 4%. And we'll continue doing this for each one of them. 96 over 300, 54 divided by 300, all the way down for all of them. This does end up getting us all of our percents. And now we have 100% of our pie chart is covered. Be aware that sometimes if you do some rounding, that these might not add up to be 100%. Maybe they add up to be 100.1 or 100.2%. That's okay. Sometimes rounding error happens, and it's not that you did it wrong. It's just that that's how it happened to round. In a case like this, we didn't need to round any of them, so we're good. The next thing we'll do then is to make the pie chart. There's a few different ways that you can do it. Some people like to start with the largest and go from there. I think that that's what we'll do this time. I do want to show you real quick that if you want to do it just in order from the top down, you can absolutely do that. I did that one a little bit ago, and it looks like this. So you can see red is 26%, blue is 4%, yellow is 32%. And that's what it looks like if you just go from the top down in no particular order. If, however, you want to do them maybe in descending order, because I think sometimes it's easier to make these when you start with the largest. So 32%, I'll make that pie chart, and it's about a third. So I don't know, I'm not great at this. You'd think I would be, but I'm not. And so we'll call this yellow, and this would be 32%. The next one I might want to make is this 26%, because that's a quarter of the pie. And so, oh, that's probably too big. There we go. That looks like it's about a fourth. So 26%, and that would be red. Notice that I'm labeling the percent and the category that it's in. Then after that, we'll do this 18% for green. And so I'll just kind of slip it up there. I just want it to be smaller than that 26%. So this is 18% green. Then we have 14%. Oops. So I'll do that. So 14%, again, it's just got to be smaller than that one. Here's orange. Then we have our 6% of none. So 6% none. And we also have 4% blue. There. So this is one way to do it, where you kind of put them in descending order. I didn't use actual colors, I just used the names, so obviously it's not as pretty. However, doing something like this does allow you to maybe see what the biggest and the smallest is right at a glance. Pie charts are great for comparing part to the whole. You can see that red makes up roughly a quarter of it. You can see that blue is very little. Okay, and then let's go back and review that other pie chart again. Again, same thing, it's just that they're not necessarily in order this way. Okay, so either one's fine. There's nothing that says they have to go in order. All right, let's go down and start looking at this pie chart. Here's one where 100 people were surveyed about their favorite beverage. How many people preferred water? Well, when we look over at our pie chart, we can see, if I try to look at the pie chart, it's tough to tell whether water or soda is more. That's really tough to tell, but because we have our little key here that tells us this is 45%, then when we want to know how many people, I will take 45% or 0.45 times the number of people that were surveyed. So 45% times 100 is 45 people. How many people preferred something other than soda, water, or juice? So soda, water, or juice. So that leaves just the other category. That's what we're looking at for this one. And that's 5%. So we'll take 0.05 times the number of people that were surveyed. If there were 500 people surveyed, we'd take 0.05 times 500. This just happens to be 100 people. How do you know that more people prefer water than soda? Well, again, that kind of comes from the key, because if you're only looking at the actual pie chart itself, it's very difficult to tell whether this blue section or whether this orange section is bigger, because those are very close to each other, right? So really, it does have to do with that key that we have. So I might say something like this. It's difficult to tell by looking at the pie. The key helps us for numbers that are close. Okay, so either that key or, like I said, a lot of times on pie charts, they'll have these labeled as well, like what percent each of these are. Um, but it's a stylistic thing. It's however you want to do. Again, pie charts are great for comparing part to the whole, to see how water compares to everything else. Hey, look, it's almost half. Next, we're going to look at some bar charts. Use the frequency table regarding favorite colors to construct both frequency and relative frequency graphs. I already did this ahead of time, but a couple things that we'll look at. These numbers all come from right here. Red was 78. So, sorry, I'm going to jump back and forth for just a minute. That's why you can see this red goes up here to 78. That's where these all came from. Blue was 12, yellow was 96, green 54, orange 42, and none was 18. So I went through and I just found where that was, and it looks like this. When I made my charts, one thing to pay attention to is I did my best to make sure that the width of each of these is about the same. None of these is particularly really fat. It's not like one is real skinny and one's really fat. And that actually does make a difference, because we have a hard time, like our eyes like to compare area. I know that sounds weird, but if I were to make one of these to be very wide and tall, and another one to be very skinny and tall, we kind of interpret this, our brain interprets this as this one being more just because it has a bigger area. Now that's not true, because this should be based on height. I'm just letting you know that I do pay careful attention when I'm making these to try to keep them all the same width. So do your best with that. Over on the right-hand side then, the relative frequency graph, this one is all of the percentages that we graphed in our pie chart. We found that red was 26%, so you can see that that's up here at about 26%. We saw that yellow was at 32%, I think it was, so you can see that went up to 0.32. One thing I also want to point out is the fact that this frequency chart here looks exactly like the frequency chart here. The only thing that's changed is our scales. Relative to each other, you can see that blue is still the smallest in both of them. You can see that yellow is still the biggest, and they still have the same shape to things. Okay, so the one on the left is just the raw counts. You can see exactly the number of people that said yellow. And on the right-hand side is the relative frequency graph, and it tells us the proportion or the percentage of people that chose each individual color. Down here we have the same pie chart is now listed in a bar chart. What percent of people surveyed prefer soda? Well, it is a little bit tough. Oh, actually, I think this is different than the one that was up above. I'm sorry. What percentage of people preferred soda? Um, it's kind of tough to tell. It looks like, I don't know, about 38. So I'm just going to say about 38%. Like I said, that is different than that pie chart from up above. Just be aware. How can you tell which beverage is preferred by the most? Well, this is very easy to tell, right? We're looking for the tallest. The tallest bar is water. So then one of the nice parts about a bar chart is you can see what the tallest is and what the shortest is right at a glance. Sometimes that's a little tough to tell in a pie chart. Now, when they are ordered in descending order, where you have the tallest on the left, and then the next tallest, and then the next tallest, and the next tallest, this actually has a special name, and it's called a Pareto chart. You don't really need to know that, but organizing them in descending order is a thing that a lot of people do. Which of these representations do you prefer for displaying the relative frequency and the frequency of the different qualitative data? This really is a preference question. There's not a right answer for this. Pie charts are great when you want to compare part to the whole, when you want to see how much something takes up relative to everything else, then that's great. Bar graphs are great for comparing sizes that are close. It's very easy for us to tell in this bar chart that water is more than soda, but that would be very difficult to tell in a pie chart because those two areas are kind of tough. They're very similar areas. Our eyes are much better at distinguishing the difference between length or how tall these are. We can see this difference much more easily than we could see the angle difference on that pie. So it really depends on what you're doing, what you prefer to do. Whether you want a bar chart or a pie chart, just depends. Next, we're going to go to displaying quantitative data. So quantitative data is numerical data, and the best way for displaying the data depends on the question being asked and how the data is structured. For example, data tables can display the numerical values without any need for category. This is just either the raw data or summary data. And then you can make dot plots. They also display numerical values, but they do show a place value overall. We'll look at a dot plot here in a minute. Histograms are typically the most common way that people display quantitative or numerical data. Histograms group the data into equally spaced categories or buckets. Sometimes you'll even call them bins. I think that's what Excel refers to them as. That's kind of what I call them. And display the frequency relative or the relative frequency. Primary difference between histograms and bar charts is that histograms represent numerical intervals, and therefore there's an actual order. You can't just put them in any order you want like you can a bar graph, okay? Line graphs are also used with data. Typically, we'll use line graphs when we want to show change over time or whether or not time is going to affect something. So let's look here. This says the table on the next page shows the daily average screen time in hours collected across 4 different seasons. Use the plots and graphs that follow to answer the questions. Well, before we actually look at these questions, I'm going to scroll to the next page and let's look at the table. So here's our data. And now we have several different graphs for us to look at. The first one is a dot plot. You can see that what we have is this is our time in hours, and one dot represents one response. For example, 2.1 would just be marked right here at 2.1, right? 3.4, they would just come over here and put a dot right on 3.4. 4.0 would be this dot right here. And they go through and make all the dots. This is called a dot plot. Some people use dots, some people use X's. Dot plots are great for showing how data is connected with each other if it's very spread apart. You can also quickly see the highest and the lowest values. Dot plots are directly related as well to box and whisker plots, which you may have heard about. We're not covering them today, but you've probably seen box and whisker plots maybe that might look like this. So if you've seen that, it's called a box and whisker. If not, don't worry about it today. Next, we have what's called a stem and leaf plot. You can see that this is tenths of an hour is what this is referred to as. And I always like to have a key. I might have a key that goes like this. I might say like 2 bar 1 equals 2.1 hours. Oops, can't spell. Hours of screen time. So that way I know that whenever, we'll say this this one right here actually has a stem of 2 and a leaf of 1. So 2 bar 1 means 2.1 hours. That key is good for any of these values. Like this one, for example, is 4 and then bar 0. That means 4.0 hours of screen time. If I want to put in 6.5, I don't know, just this one here, I will go down to 6 and then I put a 5 here. A lot of people do like to put these in ascending order as they grow out from the stem, but you don't have to. It is nice to do that, but again, it's kind of preference for what your purpose is on doing these. You can see that in total, all 30 data points, there are 30 data points here. And if you were to count all of these here, you'll see that there are 30. If there were a repeated value, we would actually list it. If there was, let's say we added one more data point and it was 8.3, I would actually put another 3 down here. And if there was another 8.3, so that there would be a total of oops, not that one. There's 1, 2, 3. If there were a total of 3 8.3s, I would actually have 3 3s down here. So I have 8 and then this bar and then 3. So just be aware that if you have repeated values, yes, we do list them in the stem and leaf plot. The next one that we're going to look at is a histogram. And I want to show you my histogram might look different than your histogram. That's because this one has been fixed. If you have a different looking one on your notes, you should probably fix it to look like this. I'm going to undo this so we can talk about all the things that were wrong with the previous histogram. So this was here before, and a couple things that are wrong with this. The first thing that you'll note is that there's spaces in between these bars. That shouldn't be the case. Another thing, the bars should be touching in a histogram. In a bar chart where those bottom numbers are categories like dog, cat, rat, fish, those are okay. They can be put in any order. Histograms where this is numerical, they need to be in ascending order like this. And we wouldn't have any spaces between our bars. That is actually very important. Also, you'll notice that 2 seems to show up in both of these categories. That's not a really good, clear way of saying this. So let's go back and look at the fixed version. Maybe. Here's a slightly different version that's a better version. It's a fixed version. So a couple other things that are different is you'll notice that the category from 2 to 4 has 9 data points in it, and that comes from the fact that up here on our stem and leaf plot, when we count everything from 2.0 up to like 3.999999, right? Not quite 4. So you can count those. There's 9 of them there. And when we look to the next one from 4 all the way up to 5.999999, but not including 6, you can see there's 10 of them there. And then when we look at the next one from 6 all the way up to 7, you can see that there's a total of 7 of them there. Sorry, 6 up through 7. And then, again, the original one actually only has 2 of them in this next category. And you might say to yourself, but wait a minute, why do we go from 8 to 10 when we only go up to 8.3? Well, we always try to keep those widths to be the same length. So this width right here is the same on all of our bars. Even if this last bar, our maximum value is only 8.3, that's okay. We're going to make that bin to be the same width as the others. So there's a slightly better looking histogram that doesn't have spaces in between, and it doesn't include those end values more than once. The last one that we're going to look at here is this line graph, and you can see that what we have is the average hours for each of our categories: fall, winter, spring, and summer. So in fall, the average number of hours was 4.43. In winter, the average hours dropped slightly, which is a little surprising, except maybe here in Arizona, people spend more time outside in the winter because it's nice. And then time went up in the spring and then back down a little bit in the summer. So a line graph is great for showing this other variable, not only the number of hours, but also based on the time of the year. So these are a couple different charts that we have. Let's go through and answer our questions as to which one we prefer for each scenario. Which graph makes it easiest to identify individual students with unusually high or low screen time? Well, just at a glance, I can tell this is the highest and this is the lowest without really any work at all. If I wanted to know what the highest and lowest was in this data table up here, I'd have to look very carefully to try to find the highest and lowest and see if there's any that are out of whack. It's a little bit easy to see over here on a stem and leaf plot, but again, this is my highest number, and this one right here, 1.8, is my lowest. The histogram, you can sort of see if you have some outliers, some numbers that seem like they don't belong, but I think the dot plot is probably our best option for that. So I would say the dot plot's the easiest to see if there are some points that are much higher or lower, because you can see the spaces in between. Which graph shows the overall distribution and shape of the data? Well, you can probably tell that just by glancing at what we have, right? Our histogram is going to be the one that shows the shape of the data the best. You can see if there are any peaks, and you can also see if there's some very low values. I do want to point out that this stem and leaf plot, if you were to look at this, it actually looks a lot like our bar chart. If we were to kind of do this and say, well, kind of looks like a little bar chart on its side where you can, if you were to turn that on its side, you could still kind of see some peaks and you could see where the low spots are. So stem and leaves also work for that, but histograms are so much more common. If you wanted to estimate the typical or the average screen time, which one should you use? Probably a dot plot or a histogram. The reason is because the balancing point is the mean. If you were to go here and if I were to say like, hey, where could you put, a little fulcrum, if we took that and just wanted to move it around, can I move it? We'll see. And if I said like, where can I put this so that this balances? Probably put it somewhere over in here a little bit, maybe. Like that's actually would be where the mean is. Same thing down here on this histogram. I know that seems kind of weird, but if I said, where could I put this so that like a little teeter-totter so that it would balance on there? Wherever we put that, that's about where the mean is. The balancing point is the mean. So I think the dot plots or histograms are best for that. If you were presenting this data to a school administrator and wants a quick summary, Which graph would you choose? Well, I would choose a histogram, and that's because histograms are very common. A lot of people use histograms, they're familiar with them, they're easy to understand. You can usually see if there's an outlier or not. This is the most commonly used graph for quantitative data. Box and whisker plots surprisingly are used quite a bit too in research from what I've found. Lastly, if you wanted to check and see which graph shows screen time, how it changes over time, the line graph is the only one that incorporates that time into this. Okay. So there's a lot of really fascinating stuff about statistics. If you also get bored, you can go and do a quick Google search for misleading statistics. There's all kinds of ways that people may try to confuse you or get you to believe something. Maybe it's to try to get you to spend your money on something. Maybe it's just to get you to advocate for something. But there's a lot of people that try to get you to believe something using misleading statistics. So having a little bit of statistical education is a good thing, and I would strongly encourage you to spend a few minutes looking up a few examples of misleading statistics so that you might see how maybe somebody might be trying to sway your opinion. Okay. Well, I hope this was helpful. I know it was fast and there's a lot there. Good luck with this. Keep practicing it. Go back over, pause, and think about some of these things. All right, good luck.